In our last segment, we explored the immense stores of heat within our planet, a legacy of its formation and ongoing radioactive decay. But how does this deep-seated energy make its way to the surface, where we can harness it? The journey of this heat involves two critical concepts: heat flow and the geothermal gradient. Heat transfer within the Earth occurs through three primary mechanisms: conduction, convection, and to a much lesser extent, radiation. Conduction is the transfer of heat through direct contact, without any material movement. In the rigid, solid rocks of Earth's crust, heat primarily moves from hotter regions to cooler ones by conduction. Imagine placing a metal spoon in a hot cup of coffee. The heat travels up the spoon through conduction. Similarly, heat from deeper, hotter crustal rocks slowly conducts its way upwards towards the surface. However, the most significant mechanism for transferring heat over vast distances within the Earth is convection. This process occurs in fluids, or in the Earth's case, in the semi-molten, ductile rock of the mantle. As material heats up near the core mantle boundary, it becomes less dense and slowly rises. As it approaches the cooler upper mantle, it cools, becomes denser, and sinks, creating vast, slow-moving convection cells. These mantle convection currents are the primary drivers of plate tectonics and efficiently transport tremendous amounts of heat from the deep interior towards the crust. While radiation plays a role in extremely hot environments, such as within the Earth's core, its contribution to heat transfer in the outer layers relevant to geothermal energy is comparatively minor. Now, let's connect heat flow to something we can measure: the geothermal gradient. The geothermal gradient is simply the rate at which temperature increases with increasing depth within the Earth's crust. It's essentially a measure of how quickly you get hotter as you go deeper underground. Globally, the average geothermal gradient is approximately 25 to 30 degrees Celsius per kilometer of depth. This means that for every kilometer you descend into the Earth, the temperature typically rises by about 25 to 30 degrees Celsius. So, at a depth of 3 kilometers, you could expect temperatures around 75 to 90 degrees Celsius, assuming a surface temperature of 0 degrees Celsius. This average gradient is influenced by the conductive heat flow through the crust. However, this gradient is far from uniform across the planet. In some regions, known as normal geothermal areas, the gradient adheres closely to this average. But in other, more interesting areas for geothermal energy, the gradient can be significantly higher, sometimes 50, 80, or even over 100 degrees Celsius per kilometer. These are called anomalous or high-temperature geothermal areas, and are crucial for viable geothermal power production. What causes these significant variations in the geothermal gradient? Several geological factors play a critical role. Firstly, plate tectonics is paramount. The highest geothermal gradients are typically found in areas of active volcanism, spreading centers like mid-ocean ridges and rift zones where molten rock, magma, is closer to the surface. These regions are characterized by a higher heat flow from the mantle, leading to much steeper temperature increases with depth. Secondly, crustal thickness and composition matter. Thinner crust allows heat from the mantle to reach shallower depths more easily. This type of rock also plays a role. Rocks with lower thermal conductivity act as better insulators, potentially leading to steeper local gradients if heat is trapped beneath them. Thirdly, and critically for geothermal systems, is hydrothermal circulation. This involves the movement of water through fractured rock formations. Cold water seeps into the ground, is heated by hot rock or shallow magma, becomes less dense, and rises. This convective movement of fluid effectively transfers heat upwards much faster and more efficiently than conduction alone, creating localized hotspots with very high geothermal gradients. The geothermal gradient is the bedrock of geothermal energy exploration. A high geothermal gradient means that economically viable temperatures for electricity generation, typically over 150 degrees Celsius, can be found at shallower, more accessible depths. This significantly reduces drilling costs and complexity, making projects more feasible. Conversely, in areas with an average gradient, reaching those temperatures might require drilling to depths of 5 to 7 kilometers or more, which is considerably more expensive and technically challenging. Understanding heat flow paths, whether through conduction in the solid crust or convection in circulating fluids, allows geoscientists to identify and characterize potential geothermal reservoirs. By mapping these gradients and understanding their underlying geological controls, we can pinpoint the most promising locations for harnessing Earth's internal heat, turning a scientific concept into a practical energy solution. Heat flow and the geothermal gradient are not just abstract geological concepts. They are fundamental guides in our quest for clean, reliable energy. They tell us where Earth's internal furnace is closest to the surface, directing our exploration efforts and unlocking the power of our planet. Next, we'll see how scientists visualize these insights through geothermal heat maps, revealing the global distribution of this incredible resource.